red guy's already 14.
We have to add this here. Samples is 1, 2, 3, 4. I know, y'all finished the tub.
The first one is already has to be
Okay. So it says we have bag of colored candy coated, and we have probability of each. For each color we have probability. Okay? So for probability of observing brown candy, we have this. It's almost 15% of the time. For red, we have 0.10. What else? Orange. We have 2, right? And then we don't have probability of green, blue. What else?
Yellow.
Yellow. Okay, so what information we have?
We have that green and brown candy probability is 0.3.
Green or
Yeah,
brown is?
0.30.
Okay, so how we can use this?
we use that formula to put the 0.3. Yeah, we struck the brown from the 0.3.
So what we can write down instead of this?
So probability
Is 0.15.
equals 0.3.
So, okay, listen. Instead of probability of green or brown, we can write down probability of green plus probability of brown equal to 0.3, correct? So now what we have, this one or this one? This one. 0.15 plus, we don't have this one yet, equals 0.3, right? And then from here you will know probability of green is 0.15. Correct? So this is one of the probability rules. We said if these two probabilities are disjoint, we can write down probability of this one plus probability of another one. Right? So now we have probability of green to be 0.15. Correct? So what else? What information we have?
The probability of not drawing the yellow candy is 0.7.
Probability of not observing yellow is
0.3
3,
or 0.7.
7. So we don't know what's the probability of yellow candy, right?
Yep.
But we know that probability of not observing an event is equal to
Or 100.
1 minus probability of observing yellow, right? 0.7. So from here, probability of yellow candy is exactly. Just one probability remain. This one. How we find this? Add them all, subtract from 1. Because we know all these together will give us probability of sample space, which is 1. Correct? So you add them all. Probability of brown plus red plus orange plus green, blue and yellow, all together should be 1. So replace each of them. We have 0.15 plus 10 plus 2 plus we don't know this, huh?
Yeah.
Plus yellow is equal 1. So probability of observing blue is 1 minus, add them all together. 0.9. 0.9. Correct? So we use almost all the probability rules. We use this probability of A or B equal to probability of A plus probability B. We use probability of not observing any event is equal to 1 minus probability of observing that event. We use the probability of sample space, which is equal to 1. Just one rule remain, which says all the probabilities are a number between 0 and 1. Just check all of them to see if you're right. If that rule also works. As you see, all of them has a probability between 0 and 1. Correct? Do you have any question? Okay, so next one. Okay, the next question says, we have four-sided die, and it can land on the whole numbers 1 through 4. So this die is a special one, has just four-sided. Correct?
pyramid diagram.
Pyramid, yeah, exactly. So let's have 4 sides. And then all of them has equal likelihood, chance. It says we have 2 of these. We are going to toss them both together, okay? So the first die can show any number between 1 and 4, right? The second die also can show any number from 1 to 4. And then we just need a combination of all of these to call that sample space, right? Sample space is the possible outcome, all the possible outcomes. So, sample space. So to do this, I will say, okay, this is the first die. Oh, actually, we have color for
it's
them.
red.
What is that?
First one's red, the second one's white.
Okay. So this one is red, this one is
White.
white. Correct? So this one can be 1, this one can be 1. 1, 2, 1, 3, right? So then actually, we have 16 of them.
Side, you could do it like sideways.
Oh, like this?
Yeah.
Yes, of course, we can do that. So 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. Do you understand this? So, for example, this one says the first die shows 3, the second die showed 1, and this is one outcome, right? And we don't have repetitive outcome at all, correct? Okay. So this whole thing is sample space, and we have how many outcomes? 16 outcomes. It says list all the combination. We did this, right? It says if the sum of the 2 outcomes on each die is recorded, what is the sample space now? Sample space will be sample space of summation. Do you remember I said gamblers are interested in adding these 2 faces and say, okay, probability of rolling 5 means observing 2 here, 3 other dice. 3 here, 2 on other. 1, 4, 4, 1. So they want summation. So now for summation, 1, 1 gives us 2 summation, right? 3, 4, 5. Do you understand this now? 3 again. 4, 5, 6. 4, 5, 6, 7, 5, 6, 7, 8. So first of all, we just we should ignore all the repetitive number we have here, right? Because some of them are repetitive. 5, 5, another 5, another 5. But as we see, all the numbers, if you want to call this a sample space, are the number between 2, 3, 4, 5, 6 we have, 7 we have, 8. And this will be the sample space they are interested in. Correct? Okay, so one thing keep in mind, please. If you find any probability, you should use this one as a sample space. You have 16 total outcome, right? Use this as a sample space, not this one. So if you want to answer any probability question, you are going to use this original sample space, combination of all the kind of faces.
So when do we use that one?
Just, yeah, whenever asked, and it's just, something to see if you understood the concept of, rolling 5, rolling 6 means summation is this much. Okay, so now this is part 2, and then what is the probability? The sum will be 4. This outcome, as you see, gives us 4, right? What else? 2, this one. 3, 1 also. That's it? So,
16.
we need event. Do you remember event was the set of outcomes that we are interested in or question asks us, right? So our event, let's call it A. Event A has 3 outcomes. And these are the only outcomes out of sample space that gives us summation 4, right?
Yes.
So now if I want to find probability of observing event A, I have just 3 outcomes here over 16. That's the reason I said if you want to find the probability, you should know how many outcomes you have in the original sample space. Correct? So this will be the probability of summation 1, 4. So now I will ask you this question. What is the probability of not observing 4? Observing summation 4. Exactly. So what you did?
Subtracted
1 minus 3 over. Exactly. Correct? So we use probability rule. Probability of not observing an event is equal to 1 minus probability of observing that event, right? Probability of not observing summation 4 is equal to 1 minus probability of observing summation 4, because this one was observing summation 4. Correct? Do you have any question?
pretty clear.
Yes.
So it doesn't matter the color, so like just for this whole thing, everything goes red first and then white, or like 1, 1,
Well,
1, 2, 1, 3.
in the question you just gave us the colors. So like if you from last class that she was giving us those probabilities, well she said dice 1 and dice 2. So this would be the same thing except they just color coded
So
it
if you
as red
don't
and white.
use the colors, you just
Yeah.
Yeah. So if it says dice 1, dice 2.
Just we are like distinguishing between them. I mean, you could call them dice 1, dice 2. I mean, call this one dice 1, this one dice 2, or this one dice 1.
They're just
Doesn't matter. Exactly. Yeah, it's just like, you know, dice 1, dice. So the next question is telling us, let's say event A is the event of observing summation equal 4. We already found it, right? But always be careful, this one is similar. But maybe in other question, they gave you another event and you should write down all the outcomes in that event, okay? It says let B be the event that the red die is 4. So now you are going to use these labels, dice 1, dice 2, or dice red dice or white dice. Now you are going to use that. B is the event that the red die is 4, means the first die is 4, showing 4. All these outcomes, correct? Right? The first die is 4, second one is 1. 4, 2, 4, 3, 4, 4. So we will write this. Is there any common outcome between these two events? Is there? So what we call this? Exactly. So event A and B are disjoint. Why? Because no common outcome. Correct? Good. These are some questions similar to your exam question. Okay. Yeah, it will be that easy. Yes.
We only have the final exam?
Just one exam remaining. Right? Chapter 12, 15, 17, 16, 17. Just this one.
Is that our finals?
Final. Any question? Yes.
So the answer of part B of the dice question would be 7. Total outcomes?
It'd be that on top.
Part 2, this one?
Yeah, so that'd be 7 total outcomes.
If the sum of outcomes on each die is recorded, what is the sample space?
Like the
Sample
size,
space is this
or
one.
the sample size, the size of it should be 7.
No, we write it down like this set. What is sample space? Set of outcomes, correct? So it's not size of sample space or number of outcomes. It's a set. When we are writing down a set, we have this curly bracket and all the outcomes we have in that set. And the outcome here is a summation of numbers on both dice, right? So all the numbers from 2 to 8. Okay. So now we are going to talk about some basic for chapter 15.
Chapter
15. Sampling distribution. Okay, so I will start with some questions. Do you remember these?
Yes.
Okay, so from the first one, tell me what is that?
Mean.
Exactly. X bar is
Mean.
mean. What is this one?
Standard deviation.
Exactly. Oops. What is this one?
Mean.
Mu is mean, right? Okay. What is this one?
Standard deviation.
Correct? So why we have two means? Why we have two standard deviation? How you can explain the difference between these two means? How you can explain the difference between two standard deviations? Think and then answer my question.
They're connected data sets.
What data set? Tell me.
So the first 2 are meant for small data sets, and the last 2 are meant for really large ones.
Good. How you can call them? What this small data set means? What that large data set means?
So a relatively small one would be one that a person could count, and the latter would be one that a computer would have to count because it's still so massive.
Can you relate this to something we recently talked about? Chapter 8 and 9.
So maybe the
Large
first,
sample.
the first one, small sample size, could be like test scores in one classroom. And then a large sample size could be test scores in the whole school.
Okay, so you said sample, right? Sample is small itself, right? So what data set was so large and we couldn't access that? Population, right? That is the large data set you are talking about. So sample versus population. This one you see we could calculate, even we had question in exam, was just some small sample size, right? Out of a population. So this one is the mean of sample. This one is the standard deviation of sample. Mu and sigma. These two I always gave you the information. You never calculated them, right?
Yes.
Because it was almost impossible to calculate them. Because these are coming from population. So this is mean of population. This is a standard deviation of population. So what we do, we use a sample to make a conclusion about our population. Sample is a smaller portion of population, right?
Yes.
So we use these two information to explain these two information because this is always known to us. This is always known to us. We can find them easily, right? But these two, most of the time, they are unknown. And in situation that we have them, we are assuming sometimes if number was this, if number was this. Do you understand? So we use these two information to interpret these two informations. So for example, we need X bar to explain mu. We need, for example, S to explain sigma. This is a statistical inference. We use some information from sample to explain our population. So now, there are two terms that we are going to talk about. Statistic parameter. A statistic is that information which comes from sample. So statistics come from sample, the information from sample, like X bar, S, we call them statistics. Parameters are the information which comes from population, like mu or sigma. So we call X bar a statistic, we call S a statistic, we call mu parameter, sigma parameter. So overall, we use a statistic to interpret parameter. Like we use X bar S to interpret mu sigma. So if you forget what is a statistic S is similar to S from sample. So these are the information comes from sample. Parameter has a similar letter as population. Do you have any questions so far? Okay, so let's read this. It says, the mean income of a sample of 98,095 households contacted by the current population survey was X bar equals 71,274. The number 71,274 is statistic because it comes from sample, right? We said X bar is a statistic. Okay. So this kind of question, like from the question, you should figure out what is explaining about sample, and you call that a statistic. Whatever explains about population, you call that parameter. Okay, in this chapter there are two important concepts that we are going to learn. One is the law of large numbers. Law of large numbers. Law of large numbers says if you increase the sample size, information of sample is going to get closer and closer to the information of population. So now we are talking about X bar. So if you increase a sample size, you know sample size is n, right? X bar tends to get closer and closer to mu. X bar comes from sample, mu comes from population. So this is the law of large number. So if you get a random sample from a population, increase the sample size over and over, mean of that sample get closer to mean of population. Let's say I want to find the GPA at UNM Gallup, and then I will have a sample of size 200, 300. I find the GPA for a student in my sample. If I increase the sample size of my students, like to 200, 300, whatever, the GPA in this sample will be closer and closer and closer to GPA of all the students, average GPA of all the students at UNM Gallup. So, average of GPA that I get from the sample is X bar. But average of GPA that I don't have it yet, and it's from population, is mu. Okay? So this is the law of large number. Do you have any question? Yes.
So what's an ideal sample size to get like closest to the real number but not being so huge?
So population size should be 20 times more than sample size, right? And then you can, convert that and say, okay, sample size should be at least this much, and convert to population. But still, there are different methods to find the sample size. In next chapter and next chapter you will see. If we have some specific margin of error, we can figure out what is the good sample size for our margin of error, and we will explain all of this next chapter. So this was the law of large numbers, and now we have central limit theorem. Okay. So, to explain central limit theorem, I need to explain the population distribution and sampling distribution. Population distribution is a distribution for parameters. These two are parameters. So the distribution of these parameters. Sampling distribution is a distribution for whatever we have in our sample. So, if you remember, previously in chapter 3, we were showing something like this. X has a normal distribution of mu and sigma, correct? So mean was mu of population, sigma was a standard deviation of population. And X was one observation from this population. Now, in this chapter, we are interested to find distribution for X bar. So, something like this, because this was distribution, right? This is a distribution of population. This X comes from population. So, we are generally talking about population, each single observation from population. But this one will be the distribution of sample mean, and the distribution will follow the same pattern, but something is different. This standard deviation here is going to be different. So this was one observation. This is the average of n observations, because you know how to find X bar, yes? So X bar is x1 plus x2 plus x3 plus xn divided by n. So average of n observations. So we are interested to find the distribution for average of n observations. Central limit theorem says, if you draw a sample size of n, same sample size, over and over and over from a population, like I have population of students, first I get a sample of size 100 from this population, another time another random sample of size 100, another time, over and over and over. If you repeat that, the average of, for example, GPA will follow a distribution which is normal. And the distribution will have this pattern, but the standard deviation will be different. And the standard deviation will be much smaller depending on the sample size you are choosing. It will be sigma over a square root of n. So this is sampling distribution. Of X bar. This mu is the mean of sample mean. It's difficult to understand, but if you just pay attention, you know the sample mean is X bar, right? I just wrote down mean. of X bar. Correct? So this is the mean of X bar. This whole thing here is the standard deviation of, can you tell me? Sample mean, right? Or you can say a standard deviation of X bar. So central limit theorem says draw an SRS of size n from any population with mean mu and a standard deviation sigma. The central limit theorem says when n is large, the sampling distribution of the sample mean X bar is approximately normal with this pattern. So this is all central limit theorem says. The sampling distribution of X bar becomes normal with this mean and this standard deviation if you choose a big sample size from population. Okay, so just as a review, first we are going to solve a question from, what was that? Chapter 3. This one. It says a bottling company uses a machine to fill the bottles with olive oil. The bottles are designed to contain 475 milliliters. In fact, the contents vary according to normal distribution with mean of 474 and a standard deviation of 3. So if we wanted to solve it using our information from chapter 3, instead of mu, we would write down, for mu we have 473, for standard deviation we have 3, correct? It says, what is the probability that a single randomly selected bottle contains less than 470 milliliters? So, how we solve this in chapter 3? We said let's start with x equals 470. Do you remember? Then we would find the z value for this x, right? 470 minus 473 divided by 3. Correct? And then we would say we want to find the area to, let's say this one is contain less than 470. Means which side? This side is less than, right? No.
It's the left side.
This left side is less than. Correct?
Yes.
We wanted to find this area. Then we would go to the table.
Yeah, I know.
So we should find the probability of z less than -1, right? Which is this one. Actually, not this one. Correct? And the area would be 0.1587, and we would say bottles. Let's see. Okay, so what we should say? Here, this one. Of bottles contain less than 470 milliliters. Correct? So this was the way we solved probability question in chapter 3. So please write this question down.
How do you know when you're supposed to use C? Just whenever asked for probability?
First of all, it's asking for probability, yes? And second, it's giving us the information about the population. It tells us the mean of the distribution. It says vary according to a normal distribution with a mean of 473 and a standard deviation of 3. Correct? So it's giving us information about the population. And as soon as we have a normal distribution for population, we are able to use this method, z-value, to find any probability. So, I want you please, so first of all, we don't have class on Wednesday, right? So write this down and try to solve as much as question you can, similar to this one from chapter 3. Go back to chapter 3, review everything. So we have you have all the Wednesday. Like we are not going to learn anything more. So go back to previous chapter 3, study everything and review everything. So on Monday, next Monday, when I'm going to solve the rest of these questions, so you will have all the knowledge from chapter 3. So you will know exactly what is table Z, how we find Z value, how we find probability, everything like that. So if I'm going to, talk about some more difficult concepts, so you already should know those easy ones, right? Do you have any question? Okay. So again, we don't have any class on Wednesday. We'll see you on Monday. We will continue chapter 15 using this central limit theorem, answer more questions, and review chapter 3. If you don't have any question, we are